And number 9, we have two populations, and this time we're looking at proportions from the two populations and comparing to see if there's a difference in the proportions from the two populations. Our first population in this example is females who recently completed high school. Our second population is males who recently completed high school. And we're comparing the proportions of people who are enrolled in college from those two groups, males and females. So our claim is that there is no difference in the proportion of college enrollees. So stated here, it would be that the two proportions are the same. So that being the same, a statement of equality, our claim is our null hypothesis that the two proportions are going to be equal. Our alternative hypothesis then would be that the proportions are not equal. You can read more about testing the difference between proportions here and see that we'll be using the normal distribution, the z-test. And also on this page, there are some good explanations of all the different symbols we'll see in our calculations and what they stand for. So since we're using the normal distribution to find the rejection region, that depends entirely upon alpha. So we'll use the normal distribution with alpha being 0.07. We had an alternative hypothesis of not equal to, which means it's a two-tailed test. So that 7%, the 0.07, needs to be divided in half. So it's split between the two tails. So we would use this formula in Excel with 0.035, 3.5%. And you get the critical value that will mark the rejection region. And you use the negative and positive of that for each of the sides. Now, if you're further to the left, if you're less than that value, you're in the rejection region. And if you're further to the right than the positive critical value, you're also in the rejection region. To find the standardized test statistic, we'll be using this formula here. And down here we have a p-bar and a q-bar, and it explains further how to calculate those. This is a weighted estimate, basically combining both of your samples together. The x1 plus x2 would be the successes from each of your samples, combine all those together. And on bottom, it's the size of each of the samples, combine all those together. So it's a weighted estimate as if you combined your samples together, what would the proportion be of that combined sample? And so that's what's going on bottom, a square root of that, and then plus 1 over, or multiplied by 1 over each of the sample sizes added together here. On top, we're basically just subtracting the proportions from each of our samples. This part here, we assume that the population proportions are equal, so this will go to 0 since they're equal to each other. So we just have this subtraction of the sample proportions is all that's on top. Doing the calculations now, we have our two sample sizes, and we were told the sample proportions. We need to find the actual successes from each sample. So what is 80% of 170? That would be 136 out of the 170 females are enrolled in college. That's where we get the 80% from. What's 68% of 150? So 68% of 150, that would mean that 102 of the 150 males are enrolled in college. That's where we get 68% from. So this weighted estimate, the p-bar that's going on the bottom of our calculation here, we're basically combining all these samples together. So pretend our sample size now is those two numbers added together. That's our total sample size here. And the number of successes is those two values added together. So what proportion of this combined sample, if we would throw both our samples together, what proportion of that is going to college? And it comes out to 0.744. 1 minus that value, we need to use that in our calculation, so I did that here. And then here I'm going to do the entire bottom part of the calculation, which we take the square root of these two values added together, the p-bar multiplied by q-bar, multiply those together, and then multiply by this sum here, which is 1 over the first sample size plus 1 over the second sample size. That B2 and C2 were my sample sizes. So add those together, and that result, you're multiplying it by P bar and multiplying it by Q bar. The square root of that entire thing. That's what goes on the bottom as we calculate our test statistic. That's on bottom. On top, we do one subtraction. It's the proportion of our first sample minus the proportion from our second sample. That's on top. This value on bottom. There's our standardized test statistic. That value is further past our critical value, so it is in the rejection region, which means we will reject our null hypothesis. Now, our null hypothesis was the claim that both proportions would be equal. And since we're rejecting the null hypothesis, there is evidence to reject the claim. In number 10, our two populations are the people from two different states. We're calling them state A and state B. And we're going to look at the proportions of people from those states who are smokers and see if there's a difference between those proportions. And our claim actually is that the proportion of adults who are smokers is lower in state A than state B. So that's our claim. There's no statement of equality here. It's that state A has a strictly lower proportion than state B. So this is going to be turned into our alternative hypothesis where the proportion from state A is less than the proportion from state B, strictly less than. That's our claim. Our null hypothesis, that's the complement of that, greater than or equal to for our two proportions. When we're testing the difference between proportions, we use the normal distribution, z-test, to find the critical values for our rejection region. We're going to use this formula for the normal distribution, plug in what alpha is, and this is a one-tailed test. It's a left-hand less than test, so Excel will give the correct critical value back. So for our given level of alpha, we have our critical value. Anything less than that, further in the left hand of the tail, will be in the rejection region. Now we need to find the standardized test statistic and see if it lies in the rejection region or not. And here's the formula we're going to be using. The information given in the problem is here. Taking those proportions, we can find the number of smokers from each sample. So 3,000 times the proportion for our state A sample. 663 out of the 3,000 were smokers. Doing the same thing with our state B sample, we find the number of smokers in our state B sample. So P bar, which we need to use in our calculation of our test statistic, is basically a weighted estimate, like we're combining these two samples together and finding the proportion of smokers from all these people combined. So the total number of people would be 6,000, those two numbers added together, and the smokers from each of the individual samples, add those together, and then you can get the proportion from those two samples combined. 1 minus that value is Q bar. We have to use that in our calculation. And so that's what I'm calculating now, is the bottom part of figuring out our standardized test statistic. It's a square root of the P bar times Q bar, these two values multiplied together, and then multiply it by 1 over each of the sample sizes added together. So in this case, it's 1 over 3,000 plus 1 over 3,000, since both sample sizes are both 3,000. Adding that together and then multiplying by these two results. Square root of that whole calculation, that is what goes on the bottom as we find our standardized test statistic. So that's on bottom. On top, we just subtract the proportion, our two sample proportions from each other. So state A minus state B on top. And here we get our standardized test statistic. And it is a positive 3.87, so it's not less than our critical value. And so it's not in the rejection region, so we will fail to reject our null hypothesis. And if we're failing to reject the null, that means there's not enough evidence to support the alternative. In this case, the alternative was the claim that the proportion from state A is less than the proportion of smokers from state B. So there's not enough evidence to support our claim. And reflecting back, this result should not surprise us. Our claim was that state A has a smaller proportion of smokers than state B. But look at the samples we got. The sample proportion from state A actually had a larger proportion of smokers than state B. So just based off these samples, it definitely doesn't support the claim that state A would have less smokers than state B.